So, here we go. We are about to start on our new chapter. This is the second chapter in the overall energy unit, I guess you'd say, here in AP Physics. And it deals with potential energy and the conservation of energy. Conservation of energy is just something that means energy does not go anywhere. It's not lost due to friction. It is conserved. And a couple other things that we want to make sure that we keep in mind before we jump into some examples that deal with this. When we're talking about work, and we're talking about force times distance. Of course, force times distance, which is equal to work, is also equal to change in energy. When you're dealing, whether you're dealing with kinetic energy, your potential energy, your spring potential energy. The thing I'd like to point out right now is that this x here, it could better be described as displacement, not distance. So, if you remember the difference between the two, if you begin here, you take this path and you end over here, this is your displacement. And that's the number that would go in for x. It would not be your total distance. It's the overall distance you've traveled, your overall displacement from the origin. If you begin in one spot and you end in that same spot, then you have zero displacement. Your distance would be whatever you went, but in this case, your displacement would be zero. So just wanted to point that out. This is also why we call energy a scalar, actually, because your displacement is a vector, has a certain direction and magnitude. Force is the same thing. It has a direction and a magnitude. And from math, when you multiply two vectors together, you get a scalar, which is why we consider energy, which is work. Work is equal to change in energy. That's why we consider energy and work scalar values. A couple other things just to point out here. When you're dealing with these conservative forces, there are two that I just want to mention right now. Generally, force of gravity is a conservative force. Of course, that's equal to mg. And the work done by gravity is going to be equal to mg times whatever distance or displacement that you travel. And of course, this is actually where we get the expression for potential energy. mgy is simply force of gravity times distance. That's the amount of work, the amount of energy change that's occurring due to gravity. And this is a conservative force. Another conservative force is spring force. And you might remember that's equal to negative kx. And the work being done by that spring is equal to 1/2 kx squared. That's your energy. So, just kind of keep those in mind. We'll be dealing with those forces quite a bit because they are conservative, which means they're going to have a big part in this chapter. Speaking of this chapter, we can't get away from calculus, so let's take care of that before we dive into some more fun things. So, conservative forces and potential energy are related by work, and a lot of this is going to be review to you. You can see right here, work is equal to the integral of force. That should come as no surprise. We talked about that in the last chapter. Down here, work is equal to your change in potential energy. So the main thing you want to know out of this is that change in potential energy is going to be equal to whatever that integral is up here. So there's a relationship between actual energy values and calculus values. So just make sure you're aware of that. In terms of what's here on the bottom, in blue, it says, and so spring potential energy is equal to the integral of force with respect to distance. What I'd like to make sure you're aware of in this is not just relegated to spring potential energy. This is also regular potential energy. But if you're dealing with regular, up-down potential energy, MGY, then this distance, this displacement in the x direction there, would actually be in the y direction. Because if you're moving vertically, changing your potential energy, you'll be dealing with distances in the y direction. But you get the idea. Usually this is done with springs, and we're dealing in the x direction. That's why I listed it that way. And the other thing to make note of, and this is all on your calculus, this is all on your AP Physics formula sheet, the slope of a potential energy versus distance graph is going to be equal to negative force. And that negative force would be equal to your spring force, your restoring force, which again is negative because it's always opposite the direction of your displacement. So, just wanted to point a few of those things out to you before we jump into a few examples of conservation of energy, which are going to come right now. So let's do that. Now, energy was the last chapter that we went through in its entirety last year before we went on our virtual COVID vacation. So hopefully some of this is reviewed to you. Conservation of energy basically means that the energy you start with is the energy you end with. So in terms of equations, they're not all that fancy. Conservation of energy simply means original energy equals final energy. There you go. So if you wanted to break this down a little bit more specifically, you could say original potential energy plus original kinetic energy is equal to the final versions of those things. And when I list the final versions, I'm not putting anything next to them. So the little zeros mean original. When there's none of that next to those letters, that means we're talking about the final potential energy, the final kinetic energy. And you could break this down even further into the individual equations. I'm not going to do that here because we'll be using those in the next example, so you'll see them quickly enough. So the example I want to take you through for conservation of energy is a pretty basic one. You've got yourself a ball. And you let it go. It's traveling downwards. So, if this is the case, we'll call this height y, the final height, off the ground, and this height here we'll call the original height. So, we'll say, to start off, that we release this ball from rest. Well, if we release this ball from rest, then it's going to fall. Should end the class right there. But let's say we want to figure out what its velocity is at any point before it hits the ground, at any height y. So if we're going to do that, we can approach that using energy equations. Use a different color. It's green time. Original energy equals final energy. So originally, let's see. We release the ball from rest. So that means there is no original kinetic energy. Of course, there is potential. At the end, it is both falling and off the ground. So we've got both kinetic and potential while it's falling. So I can break this down now into those equations. Potential energy is mgy. And that's what our equation would look like. So I want to solve for my final velocity. And before I do that, I'm just going to go ahead and make my life a little bit easier. There's all these m's all over the place. Let's just get rid of them. So there they go. If I want to solve then for my velocity, I'm just going to isolate it. So I'm going to move this gy to the other side. It'll be and then if I want to get rid of the 1/2, I got to multiply both sides by it. I'm also going to pull out this g here because it's in both places. So I'll have 2g times that equals v squared. And so if I want to get rid of the squared, I have to erase it. Goodbye, square. And if I do that, I got to take the square root of this side. And that would be my expression for final velocity. If you want to be cute about it, remember that change in means final minus original. So this is original minus final. So another way you could write this would be negative 2g change in y. If you want to make it shorter and sweeter. So yeah. And that negative, because you're flipping these, that's where that negative comes from. So that would be our final velocity at any height off the ground. Okay. So let's take this one step further. And maybe instead of releasing this ball from rest, we get very angry and we just chuck it down as hard as we can. So we no longer have an original velocity of 0. If that's the case and we want to find that final velocity at any height, we approach this problem in the exact same way that we did the last one. The only difference is now we actually have all those energies on both sides. We can't get rid of any kinetic energy at the beginning because we did not release it from rest. So we've got all sorts of energy all over the place now. So here we go. So, original potential energy. And honestly, you know, this is where the physics ends. Everything after this is just math. So, as long as you're cool with this, you're pretty well set. So, there's our fun expression. And once again, I'm going to go ahead and make my life easier by getting rid of all the m's. I have nothing against them. It's just the equation would look better without them. So, now that those m's are out of the way, I want to solve for that velocity there. Because I want to solve for that velocity, I'm going to move this whole thing over to the left so I'm looking at it from left to right instead of right to left like the last one. So again, what I did here is I got this 1/2 v squared by itself by throwing this gy to the other side. And for these two, it doesn't matter which one's on the right and on the left. What I did is I moved this 1/2 VO to the left side, but for a reason that you'll see and when we get to the end of this problem here. So this is my expression, and of course I want to take this a couple steps further. So I'm going to multiply both sides by 2 to get rid of this 1/2. And I'm going to pull out these g's. And there's our expression. And of course, we want to be cute with this, don't we? And if we do that, you're going to see kind of an interesting expression pop out of it. So again, change in is final minus original. So if this is original minus final, it's negative change in y. In other words, I can distribute that negative through. Does this look a little bit familiar? This is our time-independent velocity equation from regular physics. And so that equation actually has its source in energy equations. All of physics is one big, beautiful circle, and it's all connected. It's one of the reasons it's so much fun to teach. So if you want to finish this off, then you got to get rid of this square, and once you do that, you got to take the square root of both sides, and that would be your final expression in order to solve for velocity at any point. So there you go. All right, one more example for you here. Warning, this one's going to be a long one, and it is going to intimidate you, even more than I do. All right, I have this one pre-drawn, so that's good anyway. You're going to hate me. Check it out. Yep. We're going to solve this problem, whether you like it or not. And it's actually, believe it or not, it turns out to be not all that bad. There's a lot of math, but without the math, the physics of it is actually pretty straightforward, more or less. So let me just explain what's going to happen here. This is a mass, M6. How much can we see? Oh, you can see the whole thing when I have it resting. Good. M6 is right here, and our goal is to just barely lift M6 off that table. And the way that we're going to do that is we're going to take M3 and release it from a certain height. And as M3 swings down and picks up speed, it's going to create more tension in this string. And that extra tension, you know, if it's high enough, is going to just barely lift M6 off that table. These blue things are like little pulleys that are set in place, and everything in green is just some things that we're measuring. The red just represents the path that this mass is going to take. It's going to go down and kind of curl up. And these red dots just show this is the height off the low point that it's at right now. What we're going to try and find then is the minimum angle we need to release this mass from so that when it reaches the bottom of its path, it just barely lifts M6 off the table over there. So we have some numbers for this, thankfully, so that's nice. I'll get those out for you next. These are our numbers. I labeled the masses M6 and M3 because I set their masses equal to 6 and 3, respectively. The length, L, of the string is 1.2 meters, and that was that L on the previous picture. That's what it stood for, length of the string. And then we've got angle C, that's the critical angle, which is the angle needed to just barely lift M6 off the table. And in here in blue, this is important. Good, it looks like you can see these. I think. Yes. Oh, nope. Lame. I'm going to have to hold it up. So this first line, y original plus y1 is equal to L. You add these two lengths together, and you get the overall length of the string. I'm just going to point that out to you here. So, because this string is not changing length, when this swings to the bottom, this value here, that height, plus this value here, that height, will be equal to the length of the entire string. That's all that's saying then. This plus that will equal the length of the string. And y1 is equal to L cosine theta c. And the reason for that is because it's just using like SOHCAHTOA. When you look at y1, which is right here, and you make a triangle out of it, it is the adjacent side of this angle, so you'd use a cosine function. And when you relate this with the hypotenuse, you would get the expression that is written on that whiteboard of L cosine theta c. That's where that comes from. Now on the bottom here, you have to lift up. This little symbol here, if you're ever looking for a short way to say therefore, that means therefore, little triangle of dots. Therefore, YO, that original height that it is off the ground, is equal to L minus L cosine theta c. Because, if you substitute in y1 right here, and then you solve for that original height, this goes over there, and you get L minus y1, and y1 is equal to that. That's where that expression comes from. That's going to come in handy later. I don't think we need those numbers anymore. So, sounds like that's a tall order. Anytime it takes 4 minutes to explain a problem, you're in for quite a ride. So hold on to your seats. If we want to figure out the angle at which this needs to be in order to just barely lift M6 up off that table, it would make sense that we should really try and solve for the velocity that this object is going to have when it reaches that low point. Without that velocity, we're probably not going to get anywhere. So why don't we use some energy equations and see if we can figure out how fast M3 is going to be going at the bottom of its path. And then we'll just see where that takes us, and hopefully it doesn't take us off the mountain. So right now we're going to look for the velocity of M3 at the bottom. So we got to think about what's present in terms of energy here. Original energy equals final energy. And originally, there is no kinetic energy because it's starting from rest. You're letting it go. So all that's present at the beginning is potential energy. At the end, when it gets to the bottom of its trajectory, even with the ground, then we're just going to have kinetic energy, because its height would be 0. So this should be pretty straightforward, I think. So there's our expression. We're going to toss out the m's and multiply both sides by 2. And get rid of the square. So to get rid of the square, we erase it, and then of course we have to take the square root of the other side. Now the other thing too is, remember this YO, that original height, we actually defined already. We did that in the other whiteboard so that I won't have to do it again later. Original height is equal to length minus L cosine theta. So we're just going to toss that in right away. So there you have it. And this gets us no closer to our solution, does it? Because if we want to solve for that angle, we would need a velocity. We don't have an actual number for that velocity. So we're going to have to go somewhere else to try and figure this out. But do not forget that this velocity is equal to this expression. This expression is going to come in handy for us shortly. If we want to figure out that angle, and we want to figure out, M6, it's going to be lifting up. So what this means is if M6 is going to be lifting up, it might be a good idea to start looking at force diagrams, because we've kind of gotten to the limit of what energy can tell us. M6 is not going anywhere. It's just sitting there. So there's no real energy there. So let's jump back into force diagrams, and hopefully that takes us to a better place. So let's do M3 first. That's the difficult one. Might as well get it out of the way. So M3, we've got tension. We're looking at the force diagram of M3 when it reaches the bottom of its path. When it reaches the bottom of its path, it has tension force up, gravity down, and it's going to be equal to MA. I'm going to put little 3's next to these so I don't forget which mass I'm talking about. But this A is actually centripetal acceleration, because as it's swinging down here, it's taking kind of a quarter circle to get there. So that's interesting. Let's see what we can do with that. So force of gravity is just mg. And centripetal acceleration, of course, is v squared over r. And in this case, the length of our string is the radius. That's over L, I'll say. And that's about as far as we can take this for now. If you're thinking about plugging in that velocity from what we just did, you can do that, but we still don't have quite enough information to figure this out yet. We will be plugging that in, but let's just throw everything in at the end here. So that's what we're going to stop with for M3. In terms of mass 6, this object is sitting on that table and it's being pulled up. So tension force up minus gravity down is going to be equal to 0. Because at this point, it's just barely sitting on the table. It's not accelerating up or down. So what that means then is tension is equal to force of gravity, or m6g. And as you probably were chomping at the bit to do before, remember from the last part that our velocity is equal to two GL minus L cosine theta C under square root. So, here's what we're going to do. We're going to take tension force, put it in there. We're going to take velocity, put it in there. And now we're going to have an expression with just one unknown, the angle that we're looking for. And from there, it's just a math problem. And I'll show you the steps of it. It's rather long, but that's the end of the physics of this. So I'll write down our final expression, and then it's time to do some math. I'll use red. So tension force is m6g. And m3g. And that's equal to m3 times that velocity. Now notice this velocity is squared. So I'm just going to get rid of the square root sign. And I'm going to move the 2 out in front. Usually we put the constants out in front first. So 2 m3 times g. And there is your expression. And again, you have all these numbers except for your angle. So the first thing that I would do before doing any math with this is, and this is the point where you could just toss in the numbers right now. Although I'd say try and just look and see if there's any way that you could make your life a little bit easier here. When I'm looking, I see a lot of different ways. I see that we've got an L down here and an L in both places up there. So I can toss out the L's. And we've got G's everywhere too. So I'm going to toss out the G's too. And from there, we've got an expression that we can do some more math with and finish this problem. So that's going to wrap it up here. What I'm going to do is I'm going to put on the board the math steps that I use to get to the solution. But that's the sort of thing you guys could probably do on your own. Make sure when you're doing your math that you're distributing through everything that you need to. When I'm going from here to here, what I'm doing is I'm moving this 2m3 over there, which makes it negative And so then negative 1m3 minus 2m3 is equal to negative 3m3. That's where that comes from. Now we're getting so close. And then this last step is to plug those numbers in. And when you do all the math, you get 0.5. So if you get 0.5 for this madness here, then in order to get your angle, when you pull out your cosine, you're taking the inverse cosine. And if your calculator is properly in degree mode, and you do this correctly, you'll get 60 degrees. That is the angle at which we must release mass number 3 from, so that when it reaches the bottom of its path, it's just barely lifting mass number 6 off of the table. So there you go. And that's conservative forces. Just wait to the next video when we start talking about non-conservative forces. So take care until then. See you later.